Hello, my name is Zhihan Guo, and today I will be presenting our paper Cornus, Optimizing Atomic Commit for Cloud DBMS with Storage Disaggregation. This is a collaborative effort involving the remarkable co-authors from University of Wisconsin-Madison, Confluent, and Microsoft Research. Before we dive into the specifics, let me introduce the training architecture in modern cloud databases, which is called storage disaggregation. In this architecture, computation and storage are managed as two separate services connected by the data center network. Specifically, database logic is handled by the compute cluster, while the states of the database are stored in a cloud storage service. Such architecture allows independent scaling and billing of computation and storage, which can improve resource utilization and reduce operational cost. Moreover, it also allows people to build their system on top of existing storage services, which offers essential features such as high availability, scalability, and security at low cost. To this end, this architecture is widely deployed in more modern OLAP and OLTP systems. In a distributed database, the data is typically partitioned across different machines, and a transaction may update data in multiple partitions. When it comes to commit, the transaction must make sure the updates are applied in either all of the involved partitions or none of them. And a standard solution to this is two-phase commit, which is also called 2PC in short. Given a transaction, there is a process called coordinator, which initiates two-phase commit, and each involved partition has a process called participant that interacts with the coordinator. And I will explain how two-phase commit works using this diagram. After a transaction terminates, it asks the coordinator to start the commit process. In the first phase, the coordinator sends prepare request to each participant. On receiving the prepare request, each participant flushes the transaction's updates and locks prepared in the storage. After that, it replies to the coordinator that they are prepared. After the coordinator receives prepared from all the partitions, it locks commit and sends a commit message to all participants. At this time, the coordinator can reply to the user saying the transaction is committed. And when the participant receives the commit message, it can release the log. However, two-phase commit was originally designed for the shared nothing architecture, and it suffers from two major problems. The first one is long latency. Two-phase commit requires two network messages and two logging operations. Naively deploy two-phase commit on a cloud storage service increases the logging latency, since the storage service is at the other side of the network. And the second problem of two-phase commit is blocking. Blocking occurs if participants lost communication with the coordinator during the uncertainty period. These two problems together greatly limit the performance of two-phase commit, especially in a storage disaggregation architecture. And in this project, we propose Cornus and optimize the two-phase commit protocol for a partitioned cloud database with storage disaggregation. It has two major contributions. The first, Cornus reduced the logging latency Cornus reduced the overall latency by 1 logging latency on the critical path. Also, Cornus addresses the blocking problem we just mentioned in the two-phase commit. And the optimizations we made in Cornus rely on three capabilities in the underlying storage services. The first is the high availability of the storage services. The second is full connectivity of each compute server to storage servers. The last is the compare and swap-like functionality provided by storage services. Later, we'll show that all the existing storage services we studied have already provided those three capabilities. And next, we'll delve into how Cornice reduces latency and improves availability by leveraging those capabilities. Recall that in two-phase commit, coordinator needs to wait until the commit record is flushed to the remote log before getting back to the user. In Cornice, there's only one small change to the protocol, which avoids an asynchronous write, so that it can get back to the user before the log is flushed. But it requires some major changes in the recovery protocol. There are many failure cases to consider, and we'll just focus on the hardest and the most interesting one, which leads to the blocking in two-phase commit. As we mentioned previously, in standard two-phase commit, if a participant loses communication with coordinator during this uncertainty period, it will wait for a commit and an abort message so that it is blocked and cannot make further progress. However, in Cornice, we allow a participant to learn the fate of the transaction by reaching out to all the other participants and unilaterally abort the transaction if the decision is not ready yet. And it requires a few things to make the recovery protocol work. First, the prepare message sent by the coordinator needs to include a list of all participants' information, so that during recovery, the participants will know who to reach to in order to learn the fate of the transaction. Second, each participant's log should support a function called log_once. Given a transaction that has three stages, which are prepared, commit, and abort, the log_once updates the transaction state only if the transaction state is null. Otherwise, it returns the transaction state. Implementing such function requires a compare and swap-like API in the storage. And the third requirement is that all participants should be able to read transaction state and invoke log_once on all logs. It requires full connectivity from each compute server to the storage service. And the last requirement is the log storage should be highly available. The database service may fail, but the log does not, and that actually relies on the high availability of the log. And to summarize the participant recovery in Cornice, when a participant timeouts waiting for commit or abort, the participant can call log_once on every participant's log and try to abort whenever the transaction state is null. If all the logs returns prepared or commit, then the participant actually commit the transaction and logs the commit. If any log returns abort, then the participant can treat the transaction as aborted and logs abort. Since the storage is highly available, this will finish promptly and thereby avoiding blocking. Implementing log_once requires compare and swap on storage, which is widely supported in nowadays storage services. For example, Azure Storage modifies an object's e-tag on each update so that it can perform an update only if the update matches the object's e-tag. In Redis, we can use something called the Lua scripts that is executed by evaluate command and can be executed in an atomic and isolated way. In Amazon DynamoDB, it offers conditional puts and updates with compare and swap functionality. In GCP Bigtable, it also supports conditional writes. It worth to mention that to implement log_once, it also requires access control on logs so that a participant cannot read other participants' user data while they are trying to access or update the transaction states. This figure shows a performance comparison between CoreNAS and two-phase commit deployed over distributed Redis, where we have one master node and one slave node. And in this case, the logging time is significantly longer than the network round trip due to the overhead of replication. We can see that CoreNAS can reduce the commit latency by up to 2x compared to two-phase commit. And the latency breakdown actually shows the performance gain is due to the elimination of one logging operations in the commit phase. In the end, please check our paper for more details, which covers the pseudocode of CoreNAS, an analysis of failure and recovery. And it also provides a proof of correctness, and it's explain how to deploy a CoreNAS over Redis and Azure Blob Storage. We also provide further optimizations that can be done on CoreNAS, and also how would it be compatible with other orthogonal two-phase commit optimizations, such as early lock release. We also provided more performance evaluation against the baseline 2PC and other related works. That brings to the end of the talk. Thanks for attending the talk, and please reach out if you have any questions.